elementary transformations, find the inverse of the matrix, say A equal to 6 minus 3 minus 2, 1. What is the procedure? That first of all we consider A equal to IA. In the present case, the given matrix is 6 minus 3 minus 2, 1, and A, the unit matrix or identity matrix of second order, 1, 0, 0, 1 times A. Now, see here, do you find that the elements of first and second row are proportional? 6 multiplied by minus 3 and minus 3 multiplied, the second row. The elements of second row multiplied by minus 3 will make it first row. So in this, let's see what happens if I replace R1 by R1 plus 3 times R2. So 6 plus 3 times, say R2, that is minus 6, makes it 0, and minus 3 added to 3 also makes it 0. So both the elements of the first row become 0, keeping second row as such. On the right side, of course, you get 1, 3, 0, 1. It doesn't matter. You had noted a result, or note down again, that if during the elementary row transformations, now please note down that here by applying the transformations, all the elements of row 1, for that sake any row or column, so row 1 are 0. So we conclude that A inverse does not exist. I told you in the beginning that when we are applying elementary row or column transformations, in the process, if all the elements of any one row or column become 0, then A inverse does not exist. Now find the inverse of matrix 2 minus 3 minus 1, 2. Let me first of all write A equal to IA. The given matrix is 2 minus 3 minus 1, 2. A unit matrix of second order 1, 0, 0, 1 times A. As I told you, the first thing is to make this element A11 as 0. It is very simple. If to 2 you add 2 times the minus 1, so it will not 0. A11 you want to make it 1, so add 1s. So the first step is that you replace R1 by R1 plus R2. So by applying R1 plus R2, you get in the first row 2 minus 1, that is 1, and minus 1, keeping the second row minus 1, 2 as such. On the right side you get 1, 1, 1, 1, and second row 0, 1 as such, and A we continue to write. Now we have got this 1. Now we want to make this A21 equal to 0 with the help of A11. It is very easy if you add R2 and R1. So replace R2 by R2 plus R1. You get first row 1 minus 1 as such. In the second row you get 0 and 2 minus 1, 1. Similarly on the right side, the first row 1, 1 as such. In the second row 0 plus 1 is 1 and 1 plus 1 is 2 times A. In our next step, we wanted to make this element A22 as 1, which is automatically A11, good for us. And now finally, you want to make this element A12 equal to 0. It will be easier, you just replace R1 by R1 plus R2, because then minus 1 plus 1 will make it 0. So we get 1 minus 1 plus 1, 0, 0, 1 equal to, similarly here on the right side you add, you get 1 plus 1 equal to 2, 1 plus 2 equal to 3, second row 1, 2 as such, times A. So now which form we have got? I equal to BA. So obviously the value of A inverse is equal to B, and what is the value of B? We are calling a matrix 2, 3, 1, 2. So let me conclude that the A inverse for the given matrix A finally comes to be 2, 3, 1, 2 is the value of A inverse. find the inverse of the given matrix using elementary row transformation. The procedure is, then the first step we write A equal to IA. The value of the given matrix A is 2, 1, 4, 2. A is a unit matrix of second order 1, 0, 0, 1 into A. What do you find here? That the elements of second row are just the double that of the first. See what will happen if I say replace R2 by R2 minus 2 times R1. See what will happen. It will be the first row 2, 1 as such. In the second row 4 minus 2 times 2, that is 4 again, 0, and 2 minus 2 is 0, and of course on the right side you get 1, 0, minus 2, 1, it doesn't matter, we continue to write. So what do you observe here? That all the elements of row 2, R2, are 0, and we know that if all the elements of any one row or column during the process of applying elementary row transformations or column transformations become 0, then A inverse does not exist. So we conclude that in this case A inverse does not exist.